Hi, my name's Eric, otherwise known as Ultraviolet Man, hence the ultraviolet outfit, and today I will be discussing ultraviolet spectroscopy. So to start off, spectroscopy in general is the study of the interaction between matter and radiated energy. And radiated energy is anything like light or an X-ray or a microwave. And more specifically, UV spectroscopy is the study of how matter absorbs or reflects radiated energy that comes from the UV and visible spectral region. So the big takeaway for ultraviolet spectroscopy is that it allows chemists to measure the amount of energy a material or chemical absorbs at a specific wavelength, and that is denoted by lambda. So when we go and look at an atom that just has a valence electron shell with 2 electrons in it, this is in the ground state. This is the lowest energy here. And if we are to hit this here with some more energy, we will excite one of our electrons into our excited state here. And this is a much higher energy state. And anyway, so moving on, we can look at the applications of UV spectroscopy. Essentially, UV spectroscopy aids in the identification of certain chemical components and their constituents. So we can look at the molecular weight of an unknown compound, and that can be determined using an equation for the concentration and then converting that into molecular weight or into grams. And then we can also look at, using Beer's law, we can do materials characterization. We can also determine whether organic compounds are saturated or unsaturated, or whether they contain heteroatoms or not. And then we can also detect impurities, and we can detect functional groups. Here is our simplified version of a UV visible spectrometer. So both ultraviolet and visible spectroscopy can be performed using the same spectrometer. For visible spectroscopy, a bulb such as tungsten is used as a light source. But here in our ultraviolet spectroscopy, we're going to use a deuterium light bulb represented here. So the light source sends a beam to the diffractor, and then the diffractor breaks the beam into near, far, and extreme ultraviolet wavelengths, which are sent here to the modulator. The modulator splits that beam into 2 beams. One beam passes through a control sample, and the second beam passes through the experimental sample. The beams converge and are collected in the detector shown here. The detector then takes a ratio of absorbance values and plots them, and the dip between the absorbance values here shows the wavelength that is absorbed by the chemical sample.